Welcome to 2041. People are being told only 3 colors exist, and they believe it. And the new light nano-bot technology might just end humanity's freedom. These RGB purists are not getting away without a fight, though. You and I, we need to stop them.
Enemy positions are synced using photon transform views, whereas bullets' fire times, directions and velocities are sent on firing, so positions can be calculated locally for smooth combat even with many projectiles on screen at once. We also handle bullet and melee collisions entirely locally to prevent the player from being hit by attacks they believe they avoided in situations with high latency. There are several puzzles in the game, with the aim being to bounce a ball of nanobots towards a white door. Since you cannot combine to produce white light, it is impossible to cause the white door to swarm. Colliding the ball with the door causes the nanobots of the ball's color to fly away, leaving it unlockable. To improve the replayability of the game, the puzzles are randomly generated using a pathfinding based algorithm.
To make the control scheme easier to use, we allow color changes to be made vocally. Quick and accurate detection is provided using WebAssembly and a worker thread to increase speed and decrease impact on frame rate. We worked to prepare for any issues that may arise with access to the microphone and prepared a seamless fallback for if permission is not granted. To make a multiplayer experience that is more fun, we added optional voice features that enhance the game. Reliable voice chat, implemented using WebRTC and a custom signaling server, allows players far away to communicate strategies and to provide help to each other in difficult sections. This is done in a privacy-preserving, secure fashion. We have created a reliable system for state management, making voice chat feel like a native feature, not an add-on.
As our story features obstacles and enemies made of nanomachines, we wanted to show this off in-game using impressive visual effects. Narratively, shining brightly coloured light on objects made of nanomachines interferes with their ability to cluster, causing them to disperse and swarm around each other, with similar behaviour to flocks of birds. This system obeys 3 simple rules. Separation. Agents want to avoid colliding with other nearby agents. Alignment. Agents want to attempt to align their forward vector with that of nearby agents. And cohesion. Agents want to turn towards the average position of all other agents. For our implementation, we force agents to flock around a fixed point to prevent swarms from straying too far from their origin point. It was also required to generate points evenly across meshes of all swarmable models, and ideal to avoid computing this at runtime. This was implemented using a custom editor script to generate clouds of points which could be efficiently transformed at runtime with a single quaternion multiply. 2 variants of the script were made, one using stacked circles and one using stacked rectangles, to account for meshes of different shapes and sizes. These could both be tweaked on an object to allow you to generate a dense-looking cloud and output the number of points in the generated model.
Hi, I'm Travis, and I'm one of the composers behind Lights On. I worked closely with a team creating multiple iterations of each track to try and best capture the feel they wanted. In terms of the influences, I can best say I was heavily influenced by a lot of the soundtrack by Vangelis, Blade Runner. I was also heavily inspired by a lot of like the cheesy 80s action film soundtracks, things like, from Predator to Commando. You can hear a lot of like influence in like the production behind the track. So for example, from all the synthesizer sound design from Michael Jackson's records to the use of drum machines used by Prince. And I also looked to more modern aesthetics from EDM and dubstep artists like Skrillex. And overall, I feel like I've captured the dystopian world of Lights On with its heavy synthesized sound design, and I also had a lot of fun creating all the weird and unusual sounds with all my hardware synthesizers. It was a lot of fun.
Our game makes use of Unity's built-in nav mesh system for enemy pathfinding. This involves generating a mesh based on a scene's level topography for agents to use. However, since we make heavy use of dynamic cover in our level design, we need a way of changing the nav mesh at runtime. For this, we use nav mesh obstacles, which can carve out the nav mesh, preventing agents from passing through them when necessary.
As lighting is so central to our game, a lot of development time has gone into a system to handle it. It uses a base light color class where we define the merging rules, and a lightable object class that handles objects deciding whether or not to disappear based on the lights they're in range of. This then splits into the lightable enemy class and the lightable obstacle class. These handle the extra complexities required for enemies or obstacles to interact differently. For this to work, all enemy AI must inherit from a base enemy class, which exposes a few methods to the lightable enemy class. The lightable object in the child will look for the appropriate components in the parents, whether this be enemy logic or nav-mesh obstacles, and disable or enable them appropriately. Throughout the project, this system has been expanded upon massively, and is also heavily linked to the swarm system, as this and the enemy AI are the two things that initiate the swarming behaviour. In order to keep the players together, it was important to have a system for triggering events when they both enter a room. This was achieved by creating a modular level system that tracks the location of both players and locks and unlocks doors as the objectives dictate. If the players are on separate paths, we give the equivalent rooms the same room ID, and the system just works. One of these custom objective scripts allows level designers to place enemy objects inside of the scene, assign them with wave numbers, colours and spawn delays, and it will automatically count and handle spawning over multiple waves. We're also aware it can be incredibly frustrating to lose progress to a disconnect in a game with levels. We've made sure all the systems in the game are robust to players leaving, and in the event of a disconnect, it will pause until the other player rejoins. If necessary, it will even transfer host privileges over.
Right from the start of this project, we have emphasized a clear vision with regards to design, gathering references, concept art, memes, anything we could to ensure we all had the same clear understanding of the environment we are trying to produce. This guaranteed our asset production pipeline had a clear plan from start to finish, including modeling, texturing, shading, and animating. It was important for us that our visuals were interactive with the environment and reusable between objects. This was made possible with our very own shader programs. Visuals such as these walls, doors, or light radius indicator would not have happened without them. The outcome? Nothing short of an elegant, consistent, and clearly thought through visual experience.
Since the beginning of the project, we have used Github Actions to automate our workflows and catch bugs as soon as possible. One of the biggest challenges with this project was the unique target environment, the web. By utilizing continuous deployment, we could easily test the game in the web browser loaded from the final server. A new version was deployed every time a branch was merged into the main branch. We also only allow commits to enter main if and only if they are part of a pull request from the dev branch and all regression testing has passed. The dev branch contains in-progress and ideally working code. The regression testing suite is run via GitHub Actions against every commit to this branch. This ensures bugs are caught early on. The regression testing suite consists of two types of test: edit mode and play mode tests. Edit mode tests are assertions on the input and output of functions, whereas play mode tests are concerned with verifying the interactions of game objects within a test level. This means we could check that the light combination logic works with edit mode tests and that a player takes damage when shot via play mode tests. We also generated code coverage reports which highlighted areas of the game which have not been tested thoroughly. As well as this, it provided a crap score to highlight functions which were overly complex and should be refactored into smaller code. As well as testing the codebase, we have included tests which verify the suitability of the target platform. These include testing if the user is on a mobile device, has slow internet, or has an unsuitable WebGL version. The user is then informed of any errors found via pop-ups.
With over 1,400 Git commits, 100 plus feature branches, 1.2 million line changes, and 33 average commits per day, we are proud to present to you our team project, Lights On.